showing that host disabled participant screen sharing.
Oh, I see. Yes. I'm supposed to make you a co-host. I'm sorry. Yeah.
Okay.
And I'll also make Shivdas the co-host so that just in case I get disconnected, then he'll become the host.
Okay.
Okay, so we are live and the speaker is also the co-host now. Yeah.
Can you see the screen now?
Yes. Can you try to like
Yeah, you have to
move the slides? I'll just check if we can see your slides moving. Okay, yeah, your slides are moving, so it's all good, I think. So maybe we can start. Is it time already?
Sure.
So
Yes.
do you see the small snippet of the Zoom window on the screen, or everything is clear?
Yes. No, you will see.
Yeah, everything is clear for us actually.
Okay, because to me they're showing a small snippet of the Zoom screen. So
yes, that's normal. That's normal. That's how it should be.
Okay, so I will start now.
No,
First
just
of all,
I'll first give you the introduction. Okay. So good morning or good evening, everyone, depending on where you are. Today, our speaker is Dr. Sreetama Das. She is currently doing her postdoctoral research in University of Florence, Italy. She conducted her doctoral research in theoretical quantum information in Harish Chandra Research Institute, Allahabad, and finished PhD in 2020. Currently, she is doing her research in quantum machine learning with a significant overlap with the field of image processing. All right, over to you, Sreetama.
thank you very much, Shivdasta, for the intro. And I would like to thank you for inviting me to give this talk in TCG Crest. And I would also like to thank everyone who is present in this talk. So I will talk about one of my recent works on the experimental quantum image recognition or pattern recognition in IBMQ and NV centers. So this work has been done in collaboration with our group in Florence, which is a theoretical group, and experimental group from TU Dortmund, and it has been recently published in Quantum Machine Intelligence. So this is the outline that I will roughly follow. So I will introduce with what is quantum image processing, its scopes and applications. And then I will discuss what is swap test and how we can use swap test for quantum image recognition. And lastly, I will discuss what is quantum associative memory and how it can help us in building a quantum image recognition algorithm. So to start with, quantum image processing is when you store a classical image using quantum systems, you process it using quantum operations, and then you retrieve some classical information from that processed image. So storing means you encode a classical image as a quantum state. So there is a classical to quantum layer here, and processing is so you replace the classical operations on classical images by unitary transformations. And retrieving means that you can measure either the whole system or part of the system to get some kind of information from the obtained image, and depending which kind of classical information you want to retrieve, that will depend on your particular image processing algorithm. So why should we use quantum image processing? Because it has some advantages over classical image processing, though it is very much still in the stage of investigation, but researchers have been able to identify two main benefits. One is, of course, the higher storage capacity of qubits compared to classical bits. So suppose you have a classical image which has capital N number of pixels, but you can store that position information of those n pixels using only log n number of qubits. So this means that we need logarithmically less number of resources to store the same information. And the second one is the quantum speedup. So researchers have found that there are quantum image processing protocols which is exponentially or polynomially faster than the analogous classical protocol. So these are the main advantages of quantum image processing. So as an example, I would like to present the quantum Hadamard edge detection. So this was first proposed in this paper by Dieter Suter and his collaborators. So edge detection is when you have image of a particular object and you want to detect the edge of that object from its against its background. Of course, the edge detection applies to like all kinds of images, whether it be binary, grayscale, or color images. But in this paper, the authors chose the most simple case of a binary image. So you have this image of a cat, and then you encode this classical image as a quantum state psi. And after that, you apply your quantum Hadamard edge detection circuit on that quantum state psi. Now, for this case, for this particular protocol, the unitary circuit that we apply on psi consists of only one Hadamard gate. So after you apply the Hadamard gate, you get the state psi prime in which the edge information is encoded. Now you can either use this state psi prime for further processing, or you can retrieve some classical information from it. For example, if you want to visualize classically the edge detected image, what you have to do is just measure the state psi prime. So if you want to achieve the same thing classically, then you have to process all the pixels. So the classical image processing, classical edge detection algorithm has a complexity of the order of 2 to the power n, where 2 to the power n is the number of pixels. So quantum Hadamard edge detection is an example where you can get exponential speed up over the classical edge detection. Now, what are the possible applications?
Can I just ask a small question from the previous slide now itself? Okay, so when you do the decoding, you perform measurements, right? The quantum to classical decoding. You've got exponential number of possibilities that will arise, right? So how do you get the entire like the edge? You see what I mean? When you perform a measurement,
yeah, it is just, I mean, statistically how you construct probability from measurement. That is how you do it. I mean,
you perform some sort of sampling, I guess, on the state.
Yeah, exactly. And from the sampling, when you construct the, when you have the probability distribution, you will get the classical visualization of the edge detected image.
Okay, all right, thank you.
Okay. So image processing is a very useful task in a large number of fields, and we guess that quantum image processing can be useful in all of that. Some examples are the medical science, for example, the X-ray images or the MRI images. And another example is space science. Also recently, there is a lot of research going on autonomous vehicle engineering. So quantum image processing can be useful in all of the above fields. Some examples of the quantum image processing algorithms are, for example, quantum pattern recognition, which is the focus of this talk. Also, there is quantum edge detection, quantum image segmentation, quantum image watermarking, which is used for the security of quantum encoded images, etc. And also, I would like to mention that you can couple the quantum image processing with the field of machine learning to facilitate the quantum image classification as well. So what is quantum pattern recognition? Quantum pattern recognition is when we want to, of course, recognize a particular pattern, but that pattern can be of different types. For example, you can have a binary number string or a word, a string of texts, etc. Sometimes we are given two different images and we have to find exactly how much these images are similar to each other. And in some instances, we are given a particular image, which we will call target image, and then we are given a large data set of different other images, and we have to find the closest match of our target image. So these different instances can appear in a quantum pattern recognition. And in this talk, we will mainly focus on the second case, that is, we are given two images, which can be binary images or grayscale or color images, and we have to find the similarity between them. Okay, so as I mentioned earlier, the first step of any quantum image processing algorithm is to encode the classical image as a quantum state. And there exists a large number of different encoding methods in the literature. Here, in this work, we have used this particular method called quantum probability image encoding, which was also proposed in this quantum Hadamard edge detection paper. So what we do in quantum probability image encoding is that you encode the position information of the pixels as the basis states, and you encode the pixel values as the associated amplitudes of that basis state. So together they represent a quantum state. So for example, we have this classical image M, where we write this in a matrix notation. So 1, 1, 1, 2, 1, 3, they are just the pixel positions, and M11, M12, they represent the pixel values at those positions. And when we want to encode this image, we need only log of n square pixels. And how do we construct the chi? So we take the first column of n, and that represents the first n elements of chi, and the next n elements are taken from the second column. So we encode the image column wise, and of course we divide by the normalization factor because it has to be a quantum state. And this we choose this particular encoding method because for binary or grayscale images, it is efficient compared to the other methods, because when you encode an image using QPIE, the encoding circuit has lesser depth, so it will contribute to less noise. So that is why we choose QPIE over the other encoding methods. So now that we are equipped with the encoding, I will go to the actual protocol for quantum image recognition. So if you have any other question till now, you can ask.
One small query that so for encoding, so how many qubits you needed for encoding one image? Then for
yeah, so it depends on many factors. So as I said, here we have an image which has n by n pixels, so total n square pixels. So n square pixels, you can only the position information you can encode using log of n square number of qubits. But here in QPIE, so QPIE works only for binary and grayscale images. Okay. You cannot use it for colored images, at least not using this version of QPIE. Maybe you can devise a more advanced version. But why we can encode only binary or grayscale? Because in binary images, this M11 or M12, M13, they can be either of the two values, 0 and 1, like for binary images. And for grayscale images, this M11 or M12, they can vary from 0 to 255. So in grayscale images, the different gray shades, so there are 256 different gray shades. Okay, so if you want to represent the color, so this M11, M21, they can have different values from 0 to 255. So in QPIE, if you want to encode a grayscale image or binary image, you will need only log of 2 n square qubits. But there exist other encoding methods like FRQI or NISQ. I mean, these are very, very well-known encoding methods as well. So in that case, you do not encode the color information as the amplitudes of the basis vectors, but you represent the colors also using other qubits. So in those encoding methods, you need some qubits to encode the position information as well as some other qubits to encode the color information. But again, the color information is always, I mean, the qubits you need to encode the color, it of course does not depend on the dimension of the image. So for example, if you want to represent grayscale images in any QR, you will need 8 qubits to represent the color because 2 to the power 8 is 256. Okay, so that's why that's how it works. In QPIE, we represent only the binary and grayscale images, and we need log of n square qubits. But if you consider FRQI or any QR, you need some additional qubits to represent the color as well. Is that clear?
Yeah, it's perfect. What's about the other encoding like angle encoding or other? So those are difficult.
Yeah, I actually prepared some slides, but I did not add it to the main slides because of the time constraint. But I can talk about it probably at the end of the talk. Is that okay? Because those slides are after the yeah.
Okay, no problem.
Thank you very much. But I will come back to that. Okay, so now I will go to swap test. So swap test is a very well-known algorithm for finding the fidelity between two quantum states. So the circuit that I show in this slide considers the particular case when psi and phi, the both states are 3-qubit states. And additional to that, we have taken another auxiliary qubit, which is initiated in the state 0. And now we apply a Hadamard gate on the auxiliary qubit, and then we apply the controlled swap gates on each pair of qubits from the two states. So because psi and phi both have 3 qubits, there will be 3 controlled swap gates where the control lies on the auxiliary qubit. And finally, we apply another Hadamard gate on the auxiliary qubit, and then we measure only the auxiliary qubit. So in this way, psi and phi, they remain untouched. After we measure 0, after we measure the auxiliary qubit, if the probability of getting outcome 0 is P0, then the fidelity is given by 2P0 minus 1. So that is how you can use swap test to find fidelity between two quantum states. Now, as we have seen from the previous section that you can represent the classical images as quantum states, psi and phi. So you can just replace the states with the quantum images, and then you will find the overlap between the images. So that is how we plan to use swap test like algorithms for quantum image recognition. So if you have two images which are exactly similar to each other, then you will get the fidelity 1. And if they are different from each other, you will get a fidelity value less than 1. Now, of course, we want to test the swap test protocol in real quantum devices. And for the first case, we only use IBMQ devices. So for simplicity, let us consider that both psi and phi, they are not 3-qubit states, they are single qubit states. So we need total of 3 qubits for the swap test protocol. Now, so there will be only one Hadamard gate, one control swap gate, and then another Hadamard gate. And if we run that circuit in real IBMQ processor, what it will do is it will decompose each gate in terms of simpler gates that it can actually implement. So then the transpiled circuit will look like this. So you can see that even though the swap test has a very simple circuit, when we actually decompose it, it has a very large depth, lot of gates. So definitely it will result in a lot of noise in the outcome. So to cope up with that, so to just show you how this noisy behavior looks. So in the horizontal axis of this figure, we have shown the number of qubits, and in the vertical axis we show I mean. Now what is I? I is a quantity which we will call as the overlap, and it's just the square root of the modulus of fidelity. And I mean is when we average that overlap over 100 different instances, and sigma is the standard deviation. Okay, now we take two states psi and phi, which are exactly same to each other. I mean, they can be either both single qubit states, both 2-qubit or 3-qubit states, but they are same as each other. So we expect that when we yes.
Hi. So I would just have a question. So when you say 100 instances,
Yeah.
You mean different psi each time? Is that what you mean? You're picking different samples of your psi?
No, the psi and phi, they remain same. And of course, when we run the circuit and you measure, there will be a particular number of measurement over which you get the statistical behavior. Like if you run your computer, you have the shorts, like there is a parameter called shorts, which you can fix.
So it is over 100 shots. That's what you mean?
No. So each run is for 1024 shots, and that particular run is done for 100 times. So there is so we call one run when we have 1024 shots, and then we get the value of I, and then we repeat it for 100 times. So that is what I mean. Is that
okay? Thank you.
Okay. So we take psi and phi always to be same, and we expect that whether it's single qubit or 2-qubit states, it will always give the overlap to be 1. I mean, of course, in the real IBMQ processor, there is noise, but we still expect that it will be a value close to 1. But what we see is that for single qubit states, it has a very high value of the overlap, which is close to 0.8, which is good. But then when we increase the number of qubits to 2, it drastically decreases, and for 3 it decreases more. So we see that swap test has a very poor robustness against noise, and we can understand why, because this controlled swap gates that we use, when it is decomposed in terms of simpler gates, it actually gives a very large depth circuit. So that is why swap test contributes to more noise. Now, to cope up with that noise.
So one small query: how noise scales up with the number of gates? Just curious to know.
How noise scales up means, I mean, each gate has a particular gate noise. So if you look at the data, so if you go to your IBMQ account, and then you access each of the real quantum processors, and you want to get more information about the gates, you will see that each single qubit gate has an error, typically is of the order of 10 to the power minus 4 now. When we did this work, it was of the order of 10 to the power minus 3. It means that when you apply that single qubit gate on, say you prepare 1 qubit in the initial state 0, and you apply that particular single qubit gate on that qubit, so the outcome you get has an error of that order, 10 to the power minus 4 or 10 to the power minus 3. And for 2-qubit gates, it's more. So 2-qubit gates, the minimum error is of the order of 10 to the power minus 3 now. So that is why when you add those gates one after another, it will add up to the error. I mean, of course, it will be the error will be multiplied. Yeah.
Okay. Thanks.
Is that clear?
Yeah. Perfect. Thanks.
Okay. So to cope up with the noise in the swap test, we propose destructive swap test to be used for finding the overlap between two images. So destructive swap test circuit is equivalent to swap test circuit, but it has some differences. So we do not have an auxiliary qubit in DST, and instead of measuring only the auxiliary qubit, we measure all the qubits. But the circuit actually looks much more simpler because there is no control swap gate in DST. We have only the control NOT gates and the Hadamard gates. So now the fidelity is equal to 2p minus 1, where p, I will explain how we calculate p. So suppose when we measure all the 6 qubits here in the circuit, we will get a particular basis. So for each measurement, we will get a particular basis state. So in this example here, let's consider the first basis state 001, 101. So the first 3 bits which are colored red, they comes from psi, and the blue bits, they come from phi. And now we take the element wise AND operation for the consecutive pair of bits from the states. So we take the AND operation between 0 and 1, which gives us 0. We take the AND operation between the next pair, which is 0 and 0, gives 0. And the next pair is 1 and 1, which gives us 1. So all over, this basis state has an odd parity. In contrast to that, if you consider the basis state 101, 101, then and you do the pairwise AND operation, you will see that this basis state has overall an even parity. And now we consider all the basis states which has even parity. And these states, actually, these basis states, they contribute to the success probability. Means that if you add the probabilities of obtaining those even parity basis states, you will get this quantity called P, which we call the success probability. Okay, and now we can just calculate fidelity by using 2p minus 1. So that is how destructive swap test works. But of course, I mean, the swap test and destructive swap test, their circuit is actually, ultimately it is equivalent. So now we of course want to test how destructive swap test performs in the real IBMQ devices. And as you can see, it is much more simpler compared to the swap test. I mean, even when you decompose it in terms of simpler gates using the IBMQ basis gates, it looks much more simpler. So we can guess that destructive swap test will result in much less noise in the output. So to test that, we first use very small and very simple binary patterns. So in the figure on the top, there are four pixel images, and in the bottom figure, there are 8 pixel images. And we have a target image, which is the black square. Sorry, my cursor is not working. I don't know why. Otherwise, I would have tried to point it out. So on the top figure, the target image is a black square, and as we go from left to right, the reference figure changes. So the in each column, the left figure is the target figure and the right figure is the reference figure. So as we go from left to right, we see that the overlap between the two images is actually decreasing. For example, in the rightmost column, these two images are orthogonal to each other. That is, they have 0 overlap. Because if you represent them by using the pixel values 1 and 0, 1 for black and 0 for the white pixels, then the last images are just 1000 and 0001. So they have overlap 0. Okay, so we have calculated the overlap in 4 different ways. The green circles are for the theoretical value, and the black plus sign is the value we obtain from the IBMQ simulators. The red star is for the IBMQ real quantum processors, and sigma is the standard deviation. So, I mean, if we look at the figure for the 2-qubit images, we see that the behavior we obtain from real quantum processor is quite good. Of course, there is a gap between the ideal value and the real quantum processor value, but overall the behavior is good, because as you go from left to right, the value we obtain from real quantum processors, they decrease. And that behavior is not very clear for the 3-qubit binary images, because you see that when you vary the reference images, it does not change much. Okay, so this behavior again may appear due to the noise of the 3-qubit images, but if you compare it with swap test, you will see a very significant improvement. For example, let's look at the 2-qubit binary image here, in particularly for the case when the two images are similar. So for the real quantum processors, we have the overlap somewhat around 0.8. And now if we look at swap test, we will see that for 2-qubit images, the overlap was of the order of 0.3. So we can see a huge improvement. Also, again, let's see that for 3-qubit images, the swap test gives an overlap of the order of 0.2. But in destructive swap test, for 3-qubit images, when the images are same, then the overlap is of the order of 0.6. So it means that ultimately destructive swap test actually results in much less noise in the output. So these results were for small images. Let's consider little bit bigger images. So in this figure, we have binary patterns where each pattern is 32 by 32 pixels. So if we want to encode these images as full quantum states, we will need 10 qubits. But the problem is that the IBMQ processors that we have access to have maximum of 7 qubits. So we cannot encode these images as full quantum states. So what we do is we divide each image into 2 by 2 blocks, and now we compare the blocks from the target image and the reference image. So for example, in the first column, we compare the top image of the black square with the bottom image of the black square. They are basically same. So we take the 2 by 2 block from the top left corner of the image, and then we compare with the top left corner block of the other image. Okay, so the two blocks has to, of course, correspond to the same coordinates. And now we have all the overlap values from different blocks, and now we aggregate over all those values. And this aggregation is a little bit complicated. I will not go to the details, but it's not as simple as just summing over all the overlaps and then dividing it by the number of blocks. It's not that, because if we define it in that way, it will not capture the overlapping behavior actually. But we have been able to define a particular aggregation procedure, and by which we get the average overlap value I, which can capture the overlapping behavior between the full images. Okay, and you can see that when we actually run it in the real quantum processors, the value we get is actually in very good correspondence with the actual behavior. I mean, I'm not talking about the value itself, because of course there is a gap due to the noise, but the overall comparative behavior is same as the theoretical behavior. Okay, so this is how we overcome on one hand the size limitation, and also we get a good consistent comparative behavior between different reference images. Okay, now these were for binary images. Now we look at the grayscale images. Of course, we take two very common data sets, the MNIST images and the fashion MNIST images. So again, we do this segmentation thing, and then we get all the three different overlaps from the theoretical and from the ideal quantum simulator and the noisy quantum processors. And again, we see that for MNIST images, this behavior is really good. For MNIST fashion images, they are a little bit worse than the MNIST images. It's because, so MNIST images, though they are actual grayscale images, most of the pixels are either 0 or 1. But in MNIST fashion images, there are more shades of gray. So when you want to encode the MNIST fashion images, even like block by block, so the circuit for that encoding will be more involved than the MNIST. I mean, there will be more number of gates compared to when you encode the MNIST images. So maybe that's why it is adding up to the noise, and the behavior we get is actually worse than the MNIST images.
Why does it say MRI images of blood vessels?
I'm sorry, I forgot to change the title. So it's about the next slide. I'm sorry.
I was like, you were saying fashion images. I can see.
Yeah. I just increased the number of slides because I prepared these slides for a much shorter talk, half an hour, and then I expanded the slides.
All right, no problem.
I'm sorry. Okay, so now we consider a much more realistic scenario. For example, as I was talking about in medical image processing. So we have the image of the cross section of human blood vessel, and we want to detect if there is a cavity present in the walls of the blood vessel. So these are the images obtained from MRI, and so in the leftmost image, we just point out a small blood vessel, and which is zoomed in the image in the right. And now from that smaller blood vessel, we select different segments, and we want to detect if one of those segments match with another reference image, another target image of a cavity. So we can see that in the rightmost figure. So in each column on the left, we have a reference cavity which has been selected from maybe another image. And now we want to compare the different segments we get from our target image, and we compare it with the image of the reference cavity until we get a closest match. So I mean, this is far from accurate, of course. I mean, you can understand it's not clear how we do the segmenting and exactly how much overlap you need to confirm that yes, we have an exact match. And these are all vague things till now. But we just wanted to show that it can be a good beginning to just use the destructive swap test to find an overlap. Okay. So now we will come to the experimental verification of destructive swap test using the NV centers of diamond. So this has been done by the experimental group in TU Dortmund. I do not know much technical details about it, of course, because I'm a theorist. But just to show you the main things is that we prepare this state phi, which is basically the eigenstate of the Pauli X matrix, and then we prepare another state psi by varying this parameter theta. Now we want to see that for which value of theta the psi and phi they match. I mean, their overlap becomes maximum. So that is what we want to see. And in this case, instead of the square root of fidelity, we use the actual fidelity, because that is what you measure experimentally. So in the plots below, we have the fidelity in the vertical axis and the varying angle theta in the horizontal axis. And we see that when theta equal to pi by 2 or theta equal to 3 pi by 2, which corresponds to the actual situation for phi, then we get maximum overlap. So of course here we use single qubit states, because we did not have bigger, we did not have more than 3 NV center qubits. So that's why I could not use bigger states. It's just single qubit states, but it actually shows very good fidelity in NV center. So I mean, altogether we tried destructive swap test in 2 different kinds of quantum processors. One is IBMQ, which is made of superconducting qubits, and another is the NV center of diamond. So that concludes this section. Now I will go to the quantum associative memory part. So if you have any questions, I'm happy to answer it at this point.
It's just one query. So you said you use both for superconducting and also NV center. Mm-hmm. So what are the, I mean, difference between the result of both?
I mean, if you ask about the difference between the results,
yeah.
Okay, so as you can see, when we use NV center of diamond, of course we use single qubit states. So we have very good fidelity here. I mean, it's almost like of the order of 0.9. Right, because you have to get, if you when theta equal to pi by 2 or theta equal to 3 pi by 2, these states phi and psi, they should give you the value, ideal fidelity value 1. But here it is not 1, of course, but it is of the order of 0.9. So it is great. So it has more. So you can see that NVC actually performs better than the superconducting qubit processors.
Yeah,
because superconducting qubit processors, when we were using single qubit states, the overlap was of the order of 0.8. And here, when we use single qubit states, the overlap is of the order of 0.9. So NVC has a more improved behavior.
Very impressive, yeah. And for all this swap, this fidelity, you have calculated destructive swap test.
Yes, all of these are for destructive swap test. Yes, we just discuss swap test, but we do not, and we just as I showed in that figure here. Yeah, so this is the only experimental verification we did for swap test, because it shows so much noise. I mean, you can see when we have 2 qubits, then the fidelity between two same states actually comes down to 0.3, which is very low. So that's why we did not experiment with swap test and we shifted to destructive swap test. Okay, anything else? So I will start with a very brief introduction to quantum associative memory, the little I know about it. So associative memory is when you identify or recognize an object without accessing all the information you have about it. So for example, we can recognize a person. I mean, we do not exactly remember at which date or which time we met that person for the first time, but we recognize them. Also, for example, when we solve a crossword puzzle, you just guess a word from partial information about it. So these are examples of associative memory, and in short, associative memory is how human brain works. Okay, and also the artificial neural networks, they are designed to mimic human brain. So artificial neural networks are an example of the classical associative memory. Now, quantum associative memory was proposed in this paper by Trugenberger, and it is claimed to overcome the large storage capacity required for the classical associative memory. A very simple example of the associative memory is k-nearest neighbor method. So maybe many of you actually know what is k-nearest neighbor method. I will just shortly describe it. So in the k-nearest neighbor method, you are given a number of objects which corresponds to different class levels, and then you are given a target object to which you have to assign one of those particular labels. So what you do is you define a particular distance measure or the measure of closeness. For example, in k-nearest neighbor, you can use Hamming distance when you have the binary strings. And then what you do is you take, for example, when k, you can take any integer value for k. For example, in when you have k equal to 5, you measure the 5 closest neighbors of your target object. And when k equal to 6, you can choose 6 different neighbors. Okay, so among those 5 different neighbors, we see that majority of the objects assigned to which particular level. For example, here majority of objects actually corresponds to this orange colored labels. So we decide that we will assign that particular label to our object. I hope that was clear. I explained it very vaguely, but I hope because it is a very simple thing to understand. So this is what is k nearest neighbor method. So inspired from the k-nearest neighbor method, we can devise a protocol for quantum image recognition as well. We just replace the objects here by quantum images, and we need, of course, a measure of distance, and that measure of distance is taken as fidelity or the overlap, which we calculate using destructive swap test. Okay. So this is how the circuit looks for the associative memory based quantum image recognition protocol. So first, let me describe the circuit a little bit. So we have 4 different quantum registers. The first register consists of 3 qubits and is denoted by black horizontal lines representing the qubits. So this first register encodes the state psi, which is the target quantum image that we have to recognize. And then we are given a number of reference images. In this example, say we have 3 reference patterns, which are phi1, phi2, and phi3. So these reference patterns are encoded using the next 3 qubits, which is our second register. So these qubits are denoted with blue horizontal lines. Additional to that, we have a d-dimensional quantum system. And the dimension d will depend on how many reference patterns we have. For example, if we have 3 reference patterns here, the qubit is actually a q-treat with the basis states q1, q2, and q3. If we have n number of reference patterns, we need to take a q-nit. So the next register, which is denoted by this red horizontal line, is qubit. And lastly, we have an auxiliary qubit, which is denoted by the green horizontal line. So first, we prepare this particular superposition state between the reference patterns and the qubit. So we assign each reference pattern to a particular basis state of the qubit, and we prepare this particular superposition. Okay, this is the initial state. So initially, the first and the last register is in a product state with the second and third register. In the next step, we apply the usual destructive swap test circuit on the first and second register. So it will entangle these two registers, the first and second, while the last register is still in a product state. So what happens when you do this is that when you apply the destructive swap test is, of course, that the this first 2 registers together, they become 6 qubits, and they can stay in any possible all the possible basis states with some probability CI1, CI2, etc., where I runs over all the reference images. Okay, and in the last step, what we do is, if you remember the destructive swap test, how do we calculate the closeness between 2 quantum states? Is that we have to detect which basis states have even parity, they will contribute to the success probability, and the basis states which has odd parity will contribute to the failure probability. So to calculate the overall parities of the basis states, what we do is that we apply the CC0 gates on the pair of qubits from the target and the reference gates. Okay, so if we apply CC0 gates, what it will do is that if you have the overall parity even, then 0 will remain 0. I mean, the last auxiliary qubit on which we are actually targeting our CC0 gate. So if the basis state has even parity, then the auxiliary qubit will remain 0. But if the basis state has odd parity, then the auxiliary qubit will become 1. So after you do the final step of the CC0 gates, you can actually write the final quantum state as a sum of 2 different cases. One corresponds to the auxiliary qubit being in the state 0, and one is when the auxiliary qubit is in state 1. Okay, so, and also remember that the basis states qi, they actually corresponds to the ith image. So finally, if you measure the auxiliary qubit and the qubit, you can actually get a statistics of the particular reference image and its success and failure probability. Okay, so from that you can obtain the closest image. I mean, it will be more clear if I just show the next slide with some examples. So we have a target pattern S1, and we have 4 different patterns from which we have to detect which is closest to S1. So now we prepare this initial state. So because we have 4 reference patterns, our qubit should have 4 basis states. So we can either take a 4-level quantum state, or we can just replace it with 2 qubits, because 2 qubits also has 4 different levels. So that is why we write the initial state as this. So we have this S1 is the first register, 0 is the auxiliary qubit, and we have created this superposition state between the second and the third register. And now when we apply this circuit here on this case, we will have this image here which shows our measurement statistics. So we measure only the auxiliary qubit, and the 2 qubit which actually represents the qubit. So from the measurement statistics, we see that the highest probability is for the state 110. So 110 corresponds to the first 2 bits that corresponds to the state of the qubit, which is 11. And if you see in the initial state, 11 is assigned to S1. And this is 0 in the last bit of 110, it corresponds to even parity. So we see that the success probability of obtaining the state S1 is highest. So we can assign S1 to our target pattern. So that is where I will stop, and I will now would like to summarize what I have discussed in this talk. So we see that destructive swap test has better noise robustness when we compare it to swap test. It shows good performance for both binary and grayscale images, and we see that even when we take the segmenting approach, it actually overcomes the size limitation of the real IBMQ processors. And also it shows a good consistent behavior between different reference images, even when we use it for NISQ devices. And we see that one can have possible applications of destructive swap test in different real life scenarios, for example, in medical imaging. And also the destructive swap test can be used for the associative memory based quantum image recognition. So thank you very much. If you have more questions, I'm happy to answer. Thank you.
So, anyone has questions? Yeah, go.
Yes, actually for quantum associative memory, I think you need more number of qubits requirement will be increased, no? Compared to others.
Yes, but it is, I mean, this protocol, it means that you do not have to, I mean, each time you compare a target image with a reference image, you do not have to do it like image by image. You can just prepare the superposition state, and then you can just measure the two different quantum registers at the end. So you do not, so if you do an image by image comparison, like you take your target image and then you take each of the reference images, you have to encode them together and then measure all the qubits at the end. Because in destructive swap test, that's how it works. But if you prepare this circuit, you do not have to, first of all, you have to measure only two quantum registers, and also you do not have to do an image by image comparison. You just have to prepare this superposition state in the initial stage.
No, but since the qubit requirement will be increasing, so won't it be a practical problem for implementing this thing?
Yeah. I think, I mean, you can see, I mean, this is for the simulator, of course. We did not do the actual noise. I mean, we did not try it in the real IBMQ processors, so we do not know how the noise robustness will work. But see, the thing is, right now, in the stage in which our NISQ devices are, many algorithms are noisy. I mean, most of the quantum algorithms for which we say that there is a theoretical quantum advantage, if you simulate it in the real IBMQ processors, due to the noise, many of those quantum advantages will be suppressed. So what we wanted to present in this paper is that if you compare swap test with destructive swap test is a better tool. But even when you use destructive swap test, yes, there will be some noise. And of course, what you said is true. I mean, you have to use d-dimensional quantum systems, so you
Right.
have more noise in this circuit
More
than
qubits.
destructive swap test. That's right. So, but ultimately, when if suppose we have NISQ devices which has lower values of noise compared to the current scenario. As I said, I mean, when we did this work, the errors were of the order of 10 to the power -3 and -2 for single and 2 qubit gates. But right now it's improved. So we have gate errors of the order of 10 to the power -4 and 10 to the power -3. So as we can see that with time, the superconducting qubit devices are actually improving. And if you take a if you take a superconducting qubit which has lesser noise, you will see that ultimately it is advantageous to use this circuit compared to the image by image analysis. Because naturally in the image by image, you have to prepare the target and reference images each time, and then you have to do the measurement each time. It is more time taking than just preparing the superposition state and just do it in just one time. Like you have to measure them just one time. So compared to the image by image analysis, it's better to use the associative memory based protocol.
However, using QRAM, do you think it will be better or it will improve anything?
QRAM. I do not know much about QRAM, but what I know about QRAM is that QRAM, of course, you have not even realized QRAM till now. I mean, it's just a theoretical thing till now. I mean, we have not been able to realize it. But the advantage of QRAM in any quantum image processing is that you hope to facilitate the image encoding, because encoding a classical image as a quantum state is the first step, and this is the most challenging step actually.
Right.
And you hope to improve that using QRAM. Of
Right.
course, it has not been possible yet, but if you can improve in that stage using QRAM, then you will be able to actually get the quantum speed up of all the protocols. Okay, so that is one catch point. It's good that you mentioned QRAM. So for that, I am able to mention it, that all the quantum image processing algorithms has this one particular hitch, that when you encode the classical image as a quantum state, that the time complexity of that step can actually kill the quantum speed up. If you have QRAM, you can overcome that limitation. You can actually have the quantum speed up. But I don't know why you are saying QRAM for particular this circuit. I don't understand.
So actually,
that.
I'm just asking from the point of encoding point of view.
Okay.
Just
yeah, so that is true. If you have QRAM, then of course you in the encoding step you can actually achieve that speed up, and overall you will have the quantum advantage. Anything else?
Any other question from anyone else?
So maybe I have one more. This
Yeah,
destructive swap test. So since it's destructive, then you have to prepare the state again, or because
that's true. Yeah, in
each time you have
destructive
to
swap test you have to prepare the state again. Yeah, that is
time,
what.
yeah. So, but isn't it a problem of?
It is a problem. It is a drawback, definitely. I mean, here in this paper, we compared in terms of noise in the actual outcomes, results. But yeah, if you have to pick up one drawback of destructive swap test compared to swap test, it will be that you when you measure, you actually destroy the images, because you measure at the qubits which encode the images. So you have to prepare the images in every step. Yes, that's a good point. Thank you.
And one more thing, that you have shown that for diamond NV, the results are better than we mentioned that than superconducting quantum qubits.
Yeah.
But it's a bit surprising, because as far as I know that the coherence time of the qubits are much higher than this NV center, diamond this thing. So how come, do you have an explanation why diamond NV results are better than the superconducting qubit? Just curious to know that.
Yeah, I honestly do not have much idea about the NV centers, but what it seems that maybe in the NV center, the pulses we use to realize this rotation, okay, the pulses we use to realize this rotation, they contribute to less noise compared to the gate approach. Like the IBMQ processor are gate-based model, but here when you prepare the NV centers, you actually use the analog signals. So there can be a comparison between these two scenarios, because even the analog devices, the analog real quantum processors we have right now, they actually have better performance compared to the superconducting qubits, because, for example, there is these new devices called Pascal, which uses the analog signals, and they have better. They claim that they have a better performance compared to the superconducting qubits. But this is a good question, and I will try to find an answer to that, because I have not much idea about NVs. I do not know how that contributes to lesser noise, but I will try to find that answer.
Okay, thanks. And finally, in all your calculation, there's no need for quantum error correction. And
No, we
Quantum-
have not done that. No, we
Okay.
have not done any quantum error correction. We did an error analysis. Like
Okay.
we just wanted to vary the noise strength in the gates by using the noise simulation thing in the IBMQ processors, but we did not do any error correction. No.
Yeah, I think, Sreetama, you have another question on the chat box. Can you have a
Yeah.
look?
Okay, so I just remembered that I have to show the other encoding methods. So let me just show you the other encoding methods that are there. One of them is called the flexible representation of quantum images. I don't know how to remove this. So one is the flexible representation of quantum images, which is also sometimes called the angular representation. It's not actually same as angular representation, but what I mean is that here you use the pixel values as the angles to encode them in the quantum image. So in this example, here you have a classical image with 4 pixels, and you can use log of 4 qubits to encode the position. So you need 2 qubits to encode the position. So if you have 0 0 in the 2 qubit state, then you have the first pixel, 0 1 corresponds to the second pixel, 1 0 to the third pixel, and 1 1 the fourth pixel. And the pixel values are converted to angles. So for example, here I show color image, but if for grayscale images, if you have a grayscale image, you can convert that the pixel value to an angle by just dividing it with 250, that will be 256. So you just divide it with no, sorry, it will be 255 because there is the pixel values vary from 0 to 255. Yeah. So you divide the pixel value by 255 and then you just multiply it by 2 pi, and that is how you convert the pixel value to an angle, and then you encode it with the for the color encoding you use another qubit. So the pixel value is encoded as the amplitude of that qubit basis states. Okay, so this is called the flexible representation of quantum images, and the next one is called the novel enhanced quantum representation of images. So in this representation, the way you encode the pixel positions is same as FRQI or the QPIE that we use for our encoding. You just use the log n number of qubits to encode the pixel positions. But here, I mean, compared to the FRQI, you do not use angles to represent the pixel values. Instead of that, you use a state of qubits to represent the different color shades. So if we consider grayscale images, there are 256 values, 256 different shades, and you can encode them using eight qubits. Okay, so that is how the quantum representation in any QR looks for a grayscale image. If you have a color image, then for example, color images can also have different representations. Okay, if you consider particular RGB representations, so we have 3 different color channels, red, blue, and green, and each of the color channel can have 256 possible shades. So in total, if you use any keyword, in total you will need 24 qubits. So the first 8 qubits will correspond to the intensities of the red color channel. The second one corresponds to the green one, and the last 8 qubits, they correspond to the blue color channel. Okay, so that is why in any keyword, if you want to encode a color image, you will need 24 qubits. But this any keyword is advantageous over FRQI, because in FRQI, if you want to retrieve the classical image finally by measuring all the qubits, you have to do a large number of measurements. Okay, in any keyword, you do not have to do large number of measurements because it is deterministic. The image retrieval is deterministic. So in FRQI, you have to construct these probabilities like cos theta 0, sin theta 0. Here you do not have to construct the probabilities. You just have to get the basis states. Okay, because all the probability, all the amplitudes are same, basically one in any keyword. In FRQI, you have to construct the cos theta 0 and sin theta 0s by repeatedly measuring. So that is why we say that any keyword, it of course requires larger number of qubits, but ultimately the image retrieval is more efficient. And also, if you look into these papers, you will see that the image preparation circuit in any keyword, it has less time complexity. Then it is actually has, I mean, exponentially less time complexity compared to the FRQI. So in that sense, any keyword is a better representation than FRQI. So these are two very well-known quantum image representations. There are some other in the for example in the very initial stage of quantum image processing, there was qubit lattice encoding, etc. So there is a real Kate representation. But these usually FRQI, any keyword, and the encoding method we use, they are most widely used.
So there is something ZZ encoding. Did you try that? ZZ encoding or something?
You mean the ZZ encoding that is there in the IBMQ processors, the ZZ feature map? Do you mean that?
Right. Sorry, my microphone was off. Right.
Okay. Yeah. No. We did. ZZ encoding is actually how the QPI works, I think. I mean, ZZ encoding is not, of course, not one of FRQI or any keyword, but I think ZZ encoding is actually similar to the quantum probability image encoding that we use.
Okay.
Yeah, I think it's same, because you just want to encode the pixel values as the amplitudes of the basis states. So I think the encoding circuit is actually equivalent. They are equivalent to each other.
Any other questions?
So I have one question.
Yeah.
Sorry, I think I missed it during your talk, but what is the maximum number of CX gates that you had in your circuit?
You mean in the destructive swap-test circuit?
Yes.
So the C0 gates will depend on the dimensionality of the of your quantum image. So here in this example, if you have 3 qubit states, so each of psi and phi, they are 2 qubit states. 3 qubit states. So you need to apply a C0 to the pair of each pair of qubits from the 2 states. So here we have 3 pair of. So there will be 3 C0 gates.
Yeah, sorry. What I meant is the overall circuit. So you would have also had a state preparation circuit for psi and phi, right?
Yes. So the state preparation circuit. So for our analysis here, I mean, when we show the circuit here, we do not show the state preparation circuit. But when we actually run it in IBMQ, then you will have the state preparation circuit. When we compare the swap test and DST, we only consider the circuits for the algorithms itself, like only the destructive swap test and the swap test. We do not consider the image preparing circuit. Of course, when we simulate this circuit in a real IBMQ processor, you have to consider the image preparation circuit, but it is done completely by IBMQ processors itself. I mean, as you know, in IBMQ, you do not have to start from zero. You can just start from your desired initial state. Okay. But when you run it in IBMQ, of course, that initial state is prepared by the IBMQ processors themselves. So ultimately, it will adapt to the noise. So when we are looking at the noise behaviors here, it actually considers the image preparation also. Is that
right?
What you
So
are?
how many? Yes. But how many 2-qubit gates do you finally end up encountering in the circuit?
For example, if you see here, okay, for the image preparation, that we don't know. I mean, we did not calculate
I see.
because you have different encoding circuits for different images. So we did not compare the CNOT gates or the number of gates in the image preparation circuit. No, but you can assume that if you have simpler images, I mean, for example, if you have a binary image which looks like 1000, it will be much simple to prepare. Like you have only the state 00, so you don't do anything at all. If you have 0100, then you have to prepare the 2 qubits in the state 01. So you just have to apply Pauli gate to the second qubit. So it's like that. As you increase the complexity of the images, you need more number of gates. So that is also what I was talking about when I compared the MNIST images and the fashion MNIST images. I said that MNIST images are, though it is actually grayscale, most pixels are either 0 and 1. So it is almost like a binary image. So it's maybe the encoding circuit here is simpler compared to the fashion MNIST, which has more grayscale pixel values. So you need more number of gates to encode that the grayscale values here.
I see. Okay, thank you.
Thank you.
I think we are already 2 minutes more than the scheduled time, but it's still fine. Do you have any other questions from anyone else from the audience? If not, let's thank Dr. Sreetama Das again. We hope to have more talk. Visit our center, Sreetama, when you are here in Calcutta.
Yeah.
Visit our center. That will be our privilege.
Yeah.
All right. So, yeah, you think something?
Yeah, I look forward to meeting you all probably when I physically visit the institute.
All right, great. All right, thanks everyone.